Wait, so the last time we talked about the idea of electric fields, we spent the last week on that. And so these field lines were drawn by Faraday because he wasn't terribly good at math. But by looking at the field lines, we were able to determine how a charge would move. Basically, we could determine what the force on that charge would be without having to do any math at all. And that was really, really useful. So, as engineers, we will use this kind of technique all the time because this helps us get started on solving the problems that we want. We can draw at those field lines and go, oh, okay, well, it must be doing, something like this from here. But eventually you're going to need some numbers. And so we need to figure out how to determine the effect of this electric field on the actual particle, which means we need to calculate the electric field. And we've shown a couple of ways to do that, but oftentimes the integration gets to be really hairy unless I've got, just a nice symmetrical kind of surface like this. Fortunately, there's a better way. And in fact, you're going to find that this way is so easy, it feels like cheating. So this is called Gauss's law, and it introduces the concept of electric flux. So get your books out, make sure that you're following along. We're going to have a number of microtasks that we're going to go through with this. If you're following along with the concepts in the microtask, you're going to find that the whole thing is going to make a lot of sense to you, and you're going to be really glad that you got this. It's going to be really easy. Okay, let's get started. So the idea that we're going to use for finding this electric field is something called the electric flux. And the electric flux is the number of field lines that are penetrating any kind of surface. And it doesn't have to be a physical surface. It can be an imaginary surface. So one of the examples we're going to be looking at, let's take our parallel plate capacitor. So if this is the top plate of my capacitor and this is the bottom plate of my capacitor, then how does the field lines look? Let's say that this is positively charged and this is negatively charged, just to make it a little different. Well, the field lines, remember, are going to be drawn from the positive to the negative, and we know that in the parallel plate capacitor, it's a constant. It just comes straight down like this. So the strength of the electric field then, remember, according to Faraday's rules, is proportional to the spacing between these field lines. And, even if I draw more field lines, I've got to keep the spacing regular because it's constant in between. So what we can do is we can draw this imaginary surface here. And I'm going to color this in red. This surface right here. And it's not real. There's nothing there. However, by counting the number of field lines that go through this surface, that's the electric flux. And that gives us an actual number that we can use for defining how close together these particular lines are. So let's think about that. Let's say that I had a weaker electric field. So maybe I had only this in the same amount of time. When I draw my imaginary surface, I won't color in the solid, hopefully you can see it by now. When I draw this imaginary surface, then I'm getting fewer field lines penetrating it. That means then that the electric flux must be less, and therefore the electric field is less as well. So if we can come up with a value, a numerical value for this electric flux, that's telling us a number for Faraday's rules that we can then use to find the electric field in a very nice and convenient way. All right, so that's in general what we're going to look at. Let's take a look at the microtask 1 here. And after each one of these, I want you to stop, look at the video again, and look at your notes. And then before starting the video, make sure that you've answered each one of these. I know your temptation is just let it play. Dr. K is going to tell you what the answer is and all of that. The problem is that if you're not taking the time to think about it, you're not going to learn it. And so that's going to make it harder for you down the road. One of the really challenging things about an online class is you need self-discipline. It's easy to say, you know what, I got a lot going on in my life. That's why I'm taking this online class, because I don't have time. But you have to make the time in order to learn the material. The only difference between an online class and an in-person class is, hey, you're taking that time on your own schedule rather than somebody else's. So pause the video each time and think about each one. All right, so looking at microtask 1 then, we say, if we increase the electric field, what happens to the number of field lines going through a surface? Think about the example we just did. Pause the video, make your choice. Did you pause the video? Make sure that you did. Well, right, it's going to increase just like we saw before. It's going to increase. So the more field lines the stronger the electric field, then the more field lines I'm going to have in a particular area. They're going to be close together. Now, if I increase the size of the surface, so I'm going to keep the electric field the same, but now I'm going to increase the size of my surface, my imaginary surface that all these things are going through. What happens to the number of field lines going through that surface? Might be a good idea to do a sketch. All right, well, if you think about your sketch, if this was my first case, and I've got my field lines going through here, I'm just penetrating straight through. And then maybe these are not penetrating. If I make this bigger, I'm going to keep the electric field exactly the same. But now I'm going to make my surface bigger. And you see that now I'm capturing more of those field lines. So as I increase the size of my imaginary surface, or real surface, but then it's going to increase the number of field lines going through there. So anytime we're trying to come up with an equation, some sort of mathematical relationship between the two, we always think, does it increase, decrease, or does it stay the same? So we've decided that both of these increase. So let's take that result and let's see if we can start working on a mathematical expression for this. So how is the electric flux related to the electric field? As the electric flux goes up, the number of field lines penetrating that surface is the electric flux. What happens to the field, to the electric field? If I increase the flux, does the electric field increase? Or as I increase the number of field lines, it decreases the electric field? Pause the video and think about that. Well, sure, I'm getting more through there, so they must be directly proportional. And that tells me when I'm making a mathematical expression, that means that that electric flux needs to be in the electric flux and the electric field, both need to be in the numerator so that they'll be directly proportional. All right, how is the electric flux related to the area of the surface? As I increase the area of the surface, what happens to the electric flux? Does it increase or does it decrease? Take a look at the example that I've drawn here. It's going to increase, so they're going to be directly proportional. So again, that also has to be in the numerator. All right, so if you're not sure about that, stop the video, go back and look, because these are kind of key concepts that we're going to use for building that expression. This is a technique we're going to use all the time. Okay, so now we have decided, is it directly proportional, inversely proportional? We decided that both the electric field and the area must be directly proportional to this electric flux. So now it's time to come up with a mathematical expression for it. And this is how we always do it. We always look at how things are related. Are they directly proportional, inversely proportional? And then if it's directly proportional, it goes in the top part of any fraction bars, any fraction for the equation you may come up with. If it's inversely proportional, it's going to go in the denominator down here. All right, so let me zoom on this just a little bit so you can see a little bit better. Okay, so we need to come up with a symbol for the electric flux. Again, you can use any symbol you want, but traditionally we use the symbol phi. This is a capital Greek letter phi, and this would be the electric flux. I can have a G, and it would be the gravitational flux. And then we have decided that it is proportional to the electric field and to the area. Now, up to this point, you've always been taught that, well, electric field is a vector and area must be a scalar. It's a number, right? It's a measure on there. Well, we're going to find that's not necessarily quite the case. But before we get into that, let's say, what are the units of the flux? Anytime we define a new symbol, a new quantity, we always have to figure out what its units are. And that's very simple to do. You take any equation that you've come up with, and then you use that to come up with the expression or the units for the particular quantity you're working with. Well, we know the electric field is newtons per coulomb. Area, if we're going to do it in meters, it's going to be meters squared, if you think about it, because I have to go here times here, so that's going to be meters squared. So therefore, our units of electric flux are simply Newton meters squared per coulomb, which should look quite familiar to you. We're going to see how that works. Now, I might also have a constant proportionality. In fact, I'll always have some kind of constant proportionality. But, for example, Coulomb's constant is K is a constant proportionality. But here I'm defining the flux. So since we're defining it, we can make it be anything we want. So why make your job harder than you need to? Why not just set that constant proportionality to 1? And so that's what we do. All right. So We found up here, we decided that the electric field was a vector. We've now found the magnitude of the flux. And we know that electric field lines have a direction as well as a magnitude. Well, that's because they're vectors. So then the question is, does the electric flux have a direction? Stop the video and think about that for just a minute. So remember how we define electric flux. It's the number of lines penetrating a surface, but we don't actually care what direction those lines are penetrating for the flux. We're just counting. We're just counting the number of lines that penetrate. So that seems to indicate then it doesn't have any kind of a direction. It only has a magnitude. It's a number. And so that means that it must be a scalar, and that might be a little surprising to you. So think about why that's true. The electric field is certainly a vector. It's coming at some particular angle, but that is controlling how many of these flux lines actually penetrate the surface. But the key is that how many. I'm not looking for a direction for the flux. I'm looking for how many lines. So therefore, it must be a scalar. So let's see if we can kind of figure out what's going on with that, because this looks like this is a problem, right? I've got electric field as a vector, and I've got the area to be a scalar. So if this were correct, then this must be a vector, but it doesn't look like it's a vector. So sometimes we may assume that it's a vector, and then we'll move on. And as we think about it, we'll go, oh, wait, no, there's some properties here that show that that can't be a vector. And we're going to look more about that here. All right, so let's take a look. So here I have two diagrams, and I have two electric fields going through this surface, this Gaussian surface. And this is an imaginary surface, or it can be a physical surface. It doesn't matter. Later on, we're going to show how we can use imaginary surfaces to do some pretty cool calculations with this. So in the left-hand image, how many fields are crossing the plane, are crossing that surface? Now, remember, we define it to be crossing if it enters and exits. So it has to both enter and exit to cross it. So stop and think about that. How many lines are crossing this surface here? Well, you just count them up, and there's 5, right? So there's going to be 5 field lines that are crossing. Now look at the image on the right. How many of those are actually crossing? How many are entering and leaving the surface? Well, none of them, right? So that tells us something about the electric flux and the electric field. Let's come down here, and it says, what is the electric field in the left image? Now, we're defining the electric field, it tells you in the place up there, to be 5 newtons per coulomb. And we're doing that because it's going to be the strength of the electric field is going to be proportional to the number of lines. It doesn't have to mean 1 line equals 1 newton per coulomb, but that's a reasonable kind of proportion. So the text here tells you we're going to define the electric field here to be 5 newtons per coulomb. So what is the electric field in the left image? Well, duh, right? It's 5 newtons per coulomb. What is the electric field in the right image? And this might trick you just a little bit. There are still 5 field lines. It's the same electric field. It's just oriented this way. That's all. And so now they're all lying in this plane here. So that is also 5 newtons per coulomb. Stop and think about that. See if that makes sense to you. The field, which is a vector, has 5 electric field lines going through that surface in both cases. So I have 5 field lines, so I have 5 newtons per coulomb. Now let's talk about the electric flux. What is the electric flux? How many field lines per square meter are penetrating the surface? How many are coming in and going out in the left image? Right, so I have 5 field lines per Newton meter, per square meter here. So in each square meter, I've got 5 of these. So that flux is going to be 5. And we decided that the units are going to be Newton meters squared per coulomb, as we saw up above. Now let's look at the right image. How many of the field lines are entering and leaving that 1 square meter surface? None. So 0. This has an electric flux of 0 Newton meters squared per coulomb. And while this may seem confusing at first, this is a key concept. The electric field is there. The electric field is what it is. Those field lines are there. But if I want to know how many of those field lines are penetrating a particular surface that I design, well, then that can change. I can get from 0 to to 5. Let's go back to this same surface here, and I'm going to change my color of my pen here. Let's make it red. If I were to draw a surface this way, same electric field, but I've got the surface this way. Now how many of those field lines are penetrating the surface? Are going in and going out? 0. So you see that the electric field can be the same with the electric flux, depends upon how you've oriented this surface in here. Even though they're the same size, there's still 1 square meter for that. Okay? So let's carry on with that. Let's go ahead and delete this page here. So we had an issue, let's go back to a black pen, and we said that phi, the electric flux, was going to be the electric field times this area. But we've decided that the electric flux is a surface. I'm sorry, electric field is going to be a scalar because it's the number penetrating that surface there. So that's a problem because that would mean that A would need to be some sort of a vector so that I can take a scalar product with this. Turns out area is actually not a scalar. What you've probably your whole life referred to as the area is actually the magnitude of the area vector. There's always been this area vector. This is not something that's new. If you do computer graphics, you're making video games, or particularly if you do 3D printing, every little model that you make is composed of all these little polygons that form the surface, just little flat surfaces that come together. Each one of those polygons has an area vector that's pointing, you need it pointing outward in order for it to render correctly. And so, for example, if you have a 3D printer and you've got a polygon where the area vector is pointing in, the vector, the surface is still there, but the vector is now pointing inward. When you print it, you're going to have a hole in your model from that. So this actually has been around forever. It's just that in most cases, you don't actually care what the direction of the area vector is. You're only interested in the magnitude. We have to care. So let's look at this scenario that we have right here. So we're going to need this to be an area vector. All right, so here is my area vector. The area vector is defined to be perpendicular to the surface, always. So if I have, with my pen, if I have a surface going down this way, then it's going to be perpendicular like that. All right? So it's always defined to be perpendicular. So now if I look at the electric field, let's say it's some angle theta here, right? So the electric field is making some angle theta. That's what that little symbol is right there. So only the part that is in the same direction as the area vector is going to contribute to the electric flux. So if this, for example, let's go into red. If this, for example, is my electric field, I'm going to have a component this way, and I'm going to have a component this way. The vertical component here will contribute to the electric flux because it is parallel to the vector here. It's penetrating. The horizontal component here, it's not penetrating the surface, so it's not contributing to the electric flux. So only this component, only the component of the electric field that is parallel to the to the area vector will produce a flux. And that's just a mathematical way of saying, well, the part that's not doesn't penetrate, so it can't contribute. All right, so let's go over here. All right, so we want to come up with a mathematical expression for the part of the electric field that contributes. And basically you're asking yourself, is this the sine or is it the cosine? And so let me go back to my black pen. There. So here's my angle in this case. It's the same as the angle right here. And here is the perpendicular or the parallel component to this, which is perpendicular to the area vector. And here is the component that is parallel to the area vector. Some students get confused. They want to do it relative to the surface. We can't do that. We have to do it relative to this normal, this area vector that is perpendicular to the direction. So if this is the angle, then is the component I want the sine or is it the cosine? Stop and think about it for just a minute. Well, this one is adjacent to the area, so therefore it has to be the cosine. So that means that my electric flux must equal E, where I'm going to use a magnitude, A cosine of the angle between them. So now think back to what you know about vector multiplication. Is this the dot product or is it the cross product? Well, this is the dot product, but also we know it has to be the dot product because I need a scalar at the end of the day. So coming back to what we had over here, I have phi e equals e vector and a vector. These are two vectors, but this is a scalar. So that means I must be using the dot product here. Okay, so now we have our final electric flux, which is our final expression for it, which we did just a minute ago. So that's going to be phi e dotted into, whoops, you drew a circle there. We don't need a circle, we need a dot. There we go. Dotted in equals the electric field dotted into A. And that's going to be our definition for our electric flux, for the total electric flux going through the surface. So down at the bottom of the page, I'm going to copy it down again here. Get my camera back. I'm going to copy it down again here, but we said, just a reminder, we said that the flux, which is a scalar, is going to be E dotted with A, just like that. Let's make this camera a little bit smaller. There we go. Okay. So what I need to do, if it's a closed surface, like a sphere, or a square, or a cylinder, or something like that, then I can just go ahead and add up all those pieces. That's looking at this part right up here. So what we point out here is, instead of counting field lines, we're going to start talking about the electric flux from here on out. But remember that the flux is just the quantitative, the numerical value for this qualitative idea of how many field lines are going through the surface. All right. Now, here again, suppose it's not a square, as we've been using here, but it's some, funky curved surface. It could be a sphere, it could be a blob, it could be anything. So all we need to do is to break down that surface area into tiny, tiny pieces. Get my camera to come back. There we go. I'm going to break that surface area down into tiny, tiny pieces. So, let's say that this is my funky surface like this, right? So this piece right here, let's use a different color. This piece right here has an area vector in this direction. This piece here has an area vector in this direction. This piece here has an area vector in this direction, and so on and so on. And if my electric field maybe is going through like this, then I can say, okay, only the part right here that is parallel to the area vector counts, only the part right here that is parallel counts, and so on and so on. So I'm going to take tiny little pieces, little differential areas, so infinitesimally small areas. And that's what we mean by this dA vector. So that becomes that tiny little piece of the surface. Then I'm going to integrate over all of that surface. So we use a special integration symbol to indicate that we're doing a surface integral, not just your standard integral. And if you haven't run into this in calculus before, you will eventually. But we would say that the electric flux, which again is a scalar, not a vector, is going to be the integral over a surface. That's what that symbol means, over a closed surface. E dot dA. So I'm going to take the electric field, I'm going to take the component that is parallel to that tiny little infinitesimal piece, and this then means add them up all over the surface. And so we can't just say, oh, well, I've got my limits, I'm going from A equals 1 to A equals 10 or anything like that. I have to do this surface integral by adding all these pieces up. If I've got a generalized surface like that, that can actually be a pretty difficult thing to do. However, if I have something nice and simple, like, say, a sphere. It's my attempt at drawing a 3D sphere. Then I can add up each little piece. Well, when I add them all up, I get the area of the sphere. And while you may or may not be able to calculate that, you actually know what the area of a sphere is, right? So if you look back to your geometry, then you'll be able to say, oh, okay, wait a minute, I know what that is. So we could then say, oh, okay, I know that if I choose a surface so that E is constant, I could pull that out, and then I get the integral over this little pieces of area. So we're going to talk about that more in just a minute. All right, so suppose we want to know the electric flux through a surface with radius r, and this is the surface, so we're putting that surface at some distance away around a point charge q. Now, we already know what the field for a point charge looks like. We just did it last time. We're going to derive that in another way. And this is always a useful technique because since you know the answer, you can use this new technique and you better get the same answer because nature, the universe, doesn't care what technique you use to get there. It just says, hey, that's the answer. That's what it's going to be. And you, the human, can't change what that answer is. All right, so let's do our 5-step procedure just like we always do. So our scenario then is we're going to find the electric flux through a surface surrounding a point charge, Q. And I'll go ahead and specify that that's a point charge, just in case later on I forget. Okay, so our first step is we're going to need a diagram. Okay, well, that's pretty easy. I'm going to have my Q right there, and we'll choose our surface. Now remember, it's not a circle, it's a sphere, but I can't draw spheres. Anytime in my attempt to do so, it's going to look something like the one up at the top that I've got right here. So, and it's going to be sad. So I've drawn it as a circle, but you need to visualize it actually as a sphere surrounding that charge. And this is here's my electric field that's coming out. And again, like we did last time, I'm drawing this as a positive because if my Q is positive, this is what it's going to look like. If my Q is negative, it's going to be the same idea. It's just that my arrow is going to point inward. And then this sphere has radius r. So I'm wanting to know, what is the electric flux through that entire sphere that has radius r? That's what we're doing. So go ahead and take a minute, jot that down, get your picture, and then we'll move on to the next page. So pause the video until you're ready to go. You ready? All right. So let's go ahead and delete this one so we can move on to the next page. And I'll go ahead and erase my wonderful drawings here. Yeah, it's no secret that I can't draw, so that's fine. All right, so now step 2 is our design. So to find the flux, I have to simply use, this is E. I know that it's going to be this surface integral. Get that back where that belongs. It's going to be this surface integral here of E dot dA. Now you notice that I'm writing this down in equations. I'm writing this down in math speak. You could absolutely write this down in full terms, full English words, so that you can find it. So with the definition of the electric flux, I need to know, for the definition, I need to know what this electric field is. So my plan is then I'm going to find my electric field. And then I'm going to find out what part of this. So I'm going to find the part that is parallel to my dA. That way, that will be the only part that counts, and that's what that dot product is. If I do this well, then my E can be constant, and I can pull it out of the integral. So anytime you're working with Gauss's law, and you're working with these surfaces, you have the freedom to design this surface to be anything you want. So why not design it so that everything is a constant at that surface? Because that's going to make your job a whole lot easier. And really, fundamentally, that's the biggest part of it. Okay, so if I can get that E to come out of the integral, I'm going to be good. All right, so let's write down our symbols that we've got here. So this is what we're trying to find. And remember, that's in Newton meters squared per Coulomb, and that's the electric flux. It does not matter if you put the words describing it before or after. It's just probably a good idea to have them down somewhere so that you can keep up with it. Okay. And I also know that I'm going to need the electric field. And that's going to be something that's going to be given to me because I'm going to put that into the expression here. So I'm not going to do that with double question marks. And so that's going to be newtons per coulomb. And that's my electric field. And I also know that I'm going to need some sort of area. So that's going to be my area vector, remember. And that's going to be in meters squared. And this is the area of my surface. And that's the area of my entire surface. And remember, that's going to be a sphere for us. Okay. And then I know that Q in coulombs is my source charge. Okay. So now we're going to take a look at some equations, see if we can get this to balance out. All right. We know from Gauss's law, we know that phi is E dot A. This equation is called Gauss's law. That's it right there. So anytime somebody says Gauss's law, that's what they're talking about. All right. I know also that the force is Q times E. That would be one way. And finally, I know that the area of the sphere is going to be 4 pi r squared. And that should be everything I need. Now, maybe you didn't think about all the ones that you need. Maybe you only first thought about this. Perfectly fine. Perfectly fine. All right. So let's move on with this one and let's see how we actually go about solving this. And once you see the technique for this, it's the same over and over and over. And the very last thing we're going to talk about, I'm going to give you some rules, just a generalized procedure for figuring out how to use Gauss's law. All right. So we're going to start with, let's scroll. Now we can keep it right there and that'll be fine. So let's start with our Gauss's law equation. So this is the integral over the entire surface. Dot product, dA. So that's not just multiply, that's a dot product. All right. Let's remind ourselves what our surface looks like. So here's my charge, here's the surface, and here's my electric field lines going through it. Okay. Something like that. Okay, now the definition of the dot product, if you don't remember this, you should probably look it up, have it in your flipbook where you can get to it, because I can't take an integral until I get rid of this dot product. I need to get this in terms of magnitudes, otherwise I'm not going to be able to do it. So that's going to be the surface integral of magnitude of the electric field, magnitude of the area vector, and then the dot product is always going to be cosine theta, where theta is the angle between the electric field and the surface vector, the area vector. Well, in this case, you should notice that everywhere around this sphere, the area vector is directly parallel to the electric field. So the angle between them is 0. And the cosine of 0 is 1. And that makes sense, right? Because if they're parallel, then I should get the whole thing. If they're perpendicular, I shouldn't get anything. And so then that would be, if they're 90, cosine of 90 is going to be 0. So this term right here is going to be 1. So I'm only left with this. But the nice thing here now is I no longer have vectors. I have magnitudes. Okay. Now I can pull the E outside. Let's think about why. Because at this value of R, at this distance of R, so all along here, let's do that in another color. So all around here, do you see that the electric field is the same? Now it's not the same as I move out, absolutely. But at this distance, all of my electric field is going to be constant at that distance R. So that tells me then that I can pull this E out of the integral. And guys, that's the point. We set up our surface so that this is true, so that I can pull out the E. If you can't do that, then there's no real point in using Gauss's law. It's not going to be any easier than just doing the funky, complicated surface integrals to be able to do this. So that's an important thing to keep in mind. We want the draw my surface, you choose it, draw that surface so that the electric field is constant. All right, so now I'm going to pull that out. And so that's going to equal E. Remember, it's not a vector now, it's a scalar, integral dA, surface integral dA. Well, this is what we were talking about. If I take a tiny little bit of the surface and I integrate over that entire surface, well, guess what? That's just the magnitude of the area of that surface, the area of the sphere. And we already know what that is. That's what our equation up here is. And so that's going to be E times 4 pi r squared. Okay, so we used this before, if you remember. We can use this to get E by dividing out our test charge. We can now use what we've used before and go straight to that. That's always legal. So if you have derived, for example, the electric field of a point charge, then you can actually use that. So let's go ahead and do that instead of doing this one. So we will say that E, remember is a vector here, is equal to K. I'm going to use little q since that's the symbol I defined here. I know that in your notes it was a capital Q, but that's a shell. We always use whatever symbols I've defined here. I don't just use the shell as is. And then that's r squared. So now I can come down here and plug that in for E, and I get that the electric flux is simply going to be KQ over r squared times 4 pi r squared. And that's very interesting. The r squareds cancel. And so my electric flux then is going to be equal to K, let's put our 4 pi here first, 4 pi KQ, all of which are going to be constant. I'm not changing any of them from that. Okay. So based on our result, does the electric flux over a closed surface depend upon how far away you are from the point charge? Does R come into the problem? No, it doesn't. And that's a little surprising because we know the electric field depends upon the distance, and we know that the force depends upon the distance because of what we found up here, that F equals Q times E. So it's a little odd that the flux would not depend upon the distance. So in this case, that answer is no. So let's explore that just a little bit because that's kind of weird. But if you think about it, it also can kind of make sense. So let's draw my source charge here again. If I am a small distance away, right, then if R is very small, do you see that E is going to be very big? Because I'm close. I'm going to have my field lines are going to be much more closely spaced. As R increases, the electric field decreases. And it just so happens that because it's an area, we're talking about R squared instead of R, because it's an area. So it's meters times meters. So as the R squared goes up for the area, the R squared that's in the electric field exactly cancels that out. And so that tells me that the electric flux then is equal to a constant. That gives us an extremely important result. And that is shown down here at the bottom. And I'm going to highlight this because this is critical. This says, based on that whole derivation there, this shows that the electric flux only depends upon the total charge enclosed by your surface. And let's see if that makes sense. Because we said, okay, so here, let's say this is my charge, right? And if I draw my surface as a sphere, we all agree that it doesn't matter what radius I draw that at. So no matter what, I get the same flux here as I do here. So the amount of flux, according to our equation, can only depend upon the amount of charge that's inside there, because I can go as far out as I want. Make sure that you follow that. Well, then we said, okay, we can argue that any kind of funky shape, any parts of this, so my electric field is still going to be this way, but any parts that aren't perpendicular to that aren't parallel to the area vector, then if I have, so like for example, let's draw it right here. So here I have a component of this field line that lies along the surface right here. So that component isn't going to count. So this would normally be shorter, but somewhere else I've got to have one where the opposite case is true. If that were not true, then the surface would not close. And so you'd be able to argue that for yourself, that the surface would not close. So therefore, this is going to be equivalent to this case. If I had an open surface, yeah, then these might not cancel out. But remember, we're always drawing a closed surface around it. So the nice thing about that is it doesn't even matter what kind of surface you draw. All that matters is the total charge enclosed. The distance that surface is makes no difference whatsoever. And that's a beautiful result. So that gives us something that we can use. So the traditional form of Gauss's law, then, we define this constant here. This is called the permittivity of free space. And that's epsilon naught. We'll be using that quite a bit. Don't worry about where it comes from for now. It's one of the fundamental constants of the universe. There's three major fundamental constants of the universe, and we'll talk about where those come from. But this is one of them that deals with the electric force. And so it's defined to be 1 over 4 pi k, where k is Coulomb's constant. If you work that out, you get 8.85 times 10 to the minus 12 farads per meter. Don't worry about farads. It's actually a unit of capacitance. And we've talked about capacitors, but we'll get to defining that later on. Notice that that has to be a very small number because k is a very large number. So make sure that you can follow that. The only reason we choose this is because then I can divide out this 4 pi k that you see here. So I'm going to go ahead and write these out. Camera back on. So I'm going to go ahead and write these out. And so I have phi e is equal to 4 pi k q, and I'm going to say the charge that's enclosed. If I bring my surface down so that it is inside this, then not all of the charge might be in there, and so then the flux would be a little bit different. But I can also do it so that, for example, what if I have several charges in play, like we've used before? So I could have one here and one here and one here and one here. Well, I could draw a surface around this, a sphere, hopefully, because that's easy to integrate. And then the total charge is just Q1 plus Q2 plus Q3 plus Q4. That's the charge enclosed. No math to solve, just add them up, plug it in right there. Well, I want to make my formula a little bit prettier by replacing this with the permittivity of free space. And when I do that, then I'm going to get this result right here, that phi e is equal to the Q enclosed divided by this epsilon naught, this permittivity of free space. And that's the traditional form of Gauss's law. But you also know that Q enclosed over epsilon naught must be equal to the surface integral of E dotted into A. Most of the time, we're using this idea of a flux to get the electric field. But I don't actually have to calculate a number for the flux, do I? Because the flux by Gauss's law is Q enclosed over epsilon naught. That's a constant. That's something that I can just count up how many charges are in there. So if I choose my surface to be something easy to integrate, like a sphere or a cylinder or a plane or something like that, something that I can get the area of very easily, then I can, and if my E is constant on that surface, very important, then I can pull that E out and I'll get integral dA, which is just going to be the area. So you take this value, Q1 plus Q2 plus Q3 plus Q4, divide by the area of that surface, divide by the area of the sphere in this case, boom, you've got the electric field. So that is a very, very, very useful result that we can have for this. All right, let's sum up some of this. Let's zoom out and come back up here. We'll turn the camera back on in a second. So this is our procedure for using Gauss's law. Let me erase what we've got done. Whoops, not the ruler. Let me erase what we've got here so that we've got some room to work with. Okay, so we draw a nice, easy to integrate symmetrical surface. This is the art to using Gauss's law. You, the engineer, you, the physicist, you get to choose what surface you want. So why not make it something easy? Make it something that you can integrate very easily, because what you're looking for is the area of that Gaussian surface that you've drawn around there. It's an imaginary surface, and it feels like you're cheating because you're like, well, you know, I can draw this to make it easy. Why not? So I might have something like, let's do our example here. We had Q1, we had Q2, and Q3, and maybe one over here is Q4. So what I would do then is I would draw a spherical Gaussian surface that covers that entire bit. So now I know the flux is always the total charge enclosed, Q1 plus Q2 plus Q3 plus Q4, divided by epsilon naught. And I know that that's equal to the definition of the electric flux, which is the integral of E dot dA. Since my flux is going to be constant, I can pull it out of the integral and then integrate this, and I can get my total area. Let's take a very simple result that'll convince you that this is true. One that we've done before. So we're going to take our point charge. So let's say that I've got a point charge Q. All right. I'm going to draw my Gaussian surface. And I'm going to say this, let's see, this has radius R, for example. And I'm going to say, okay, I will draw on that surface. So now I know that Q enclosed, which in this case is just Q, divided by epsilon naught, must be equal to the integral E dot dA. Now I've chosen my surface so that that electric field is always going to be perpendicular. And it's always going to be constant. So I'm going to pull that out, and I get Q over epsilon naught equals E dotted, or integral, sorry, dA. Well, the surface integral of dA is just the area. And so I get Q over epsilon naught equals EA, which equals E 4 pi R squared. So to get the electric field then, all I have to do is divide that out. And so I get Q over epsilon naught 4 pi R squared is equal to A. And you say, wait a minute, that's different. Well, remember that epsilon is 1 over 4 pi K. So I'm going to rewrite that because epsilon naught is 1 over 4 pi K. So if I substitute that in right here, the 4 pi is going to come on the top, and so is the K, times Q divided by 4 pi R squared. And look at that. Magic. I've got the same one that I had. So now one thing you might justifiably complain about is, what if I have this and I've drawn this, but my electric field is not going to be constant? Well, that's the Q enclosed, but if the field might be stronger out here than it is over here, because remember, than it is, say, right here in the middle, because remember, it's a vector. I'm going to have to add up all of those. So it may be that I haven't drawn a surface around here where my E is constant. I still could use this, but now I can't bring the E outside of the integral because it is the charge that's enclosed. That absolutely will work. But I can't bring my E outside the integral because it's not constant. Get the camera back. There we go. Because it's not constant. So I would have to figure out, okay, how can I integrate what E is around that little surface? Might be better if I could find some surface that fits it, that I can still find the area of, but now it's all constant, that it's always, say, perpendicular or always at a fixed angle, something like that. Then I could go with it. But you're going to find that a lot of times with a configuration like this, yes, I can absolutely find the total charge enclosed, but the electric field isn't constant. And so the work that I do is no easier than doing it the long way without the electric flux. I'm doing the same amount of work, so you don't really gain anything with that. So that's going to be part of the art, is you want to look at the situation and say, okay, is this a situation where I can use Gauss's law to some sort of benefit? And if you think about our parallel plate capacitor, let's just look at one of these. So I've got some charge Q on this plate. And you remember it was either positive or negative. We'll go ahead and make that Q. So what kind of Gaussian surface might I want to do? Well, you might say, well, no, a sphere is not going to be really good because my electric field, remember, is going to look like this. So drawing a sphere around there wouldn't be a good idea because it's not going to be constant everywhere around here. What I could draw, however, is a cylinder going through the plane like this. So you see that the sides of the cylinder are parallel to my surface, my area vector. My area vector is going to be right here because it's perpendicular. So the E field is parallel to the sides, which means that it's perpendicular to the area vector. Well, what is the dot product of this part? It's actually 0. So these sides don't contribute anything at all. So all I need to worry about, of course, I'm going to have electric field coming out the other side too, because I might have something down here. But anyway, just from the charges. So all I need to do then is say, okay, how much of the field is going through this surface area and how much is going through this, and I add them up. And that's all I need. So if I know how much Q is contained in that part right there, that's the Q that's enclosed. The rest of this isn't enclosed, so I don't need it. Only this part in here. So that would be my Q enclosed, like we've shown here. But now my E field is constant as it comes out through this. And so I can pull that outside, and then I just add up my two areas. They're vectors. So I just add up my two areas. The area of a circle, you obviously probably already know, is pi r squared. So I would just add up the pi r squared for the top plus the pi r squared for the bottom. And in this case, they're going to be the same value. Times E is going to equal to the Q enclosed, which is just this part of it right here, over epsilon naught. Take this, divide by this, and I've still got my electric field. And so that's going to be an easy way that I could get the electric field. Point being here is the art of drawing the surface is where the challenge to using this technique is, and figuring out, what kind of surface can I do? And it requires some creativity. So you're going to get some practice with this in your homework problems. But as always, if you have any questions at all, make a discussion post and let's talk about it. Because this is not like math where you can just sit there and turn a crank and something's going to come out. You have to get creative with this. And once you start to get good at it, it's actually kind of fun. It's not bad. Creativity is always fun. But at the very beginning, it can be a little frustrating to try to follow it because you just don't have enough examples to see what we're talking about here. Do the homework. The practices will take you through it, and you'll feel a lot better about it. All right? Gauss's law is a critical tool for what we're going to be doing. So much so that your next section that you're going to be doing is nothing but using Gauss's law and giving you some of those examples for how we can apply it to what we're working with. Because as I said a few minutes ago, the art is coming up with that surface, and finding that Gaussian surface is going to make my job easier. If I'm not making my job easier, well, then what's the point? I'm just going to do the differential equations, solve the math, and go with it. So if you're feeling a little uncomfortable with it right now, that's okay. What you need is practice. What you need is being able to see the different examples, and it'll start to all gel into place. But be sure and post a discussion. Let's get some people talking back and forth about this, because the more you can help each other, the better off you're going to be. And obviously, I'm going to be reading those discussions as well, and I'll contribute to that. All right, we'll see you next time.